Here's a quick explanation of horizontal displacement of projectiles and the factors that affect horizontal displacement. So horizontal displacement is really just a fancy word for how far something or a projectile travels. It says on there it's the shortest distance a body travels from the start to the finish in a line parallel to the ground. So we tend to talk about horizontal displacement when we're talking about projectiles, things that we throw. So it could be a shot put, it could be a ball, it could be a body. If we look at the guy there, the shot putter, the horizontal displacement would be from the point that the shot is released from the hand to its landing point. So horizontal displacement, the shortest distance a body travels from start to finish in a line parallel to the ground. There are three key factors that affect horizontal displacement, and for the exam you'll need to be able to explain these factors but also apply them to different situations as well. So I'm going to give you a second if you want to pause the clip in a moment just to write down on your revision sheet or your mind map or whatever it is that you're using, what are the three key factors that affect horizontal displacement? In other words, how far something like that shot put would travel, plus a brief explanation. And if you pause it, you can then come back and I'm going to explain it to you. So you should have identified the three key factors as height of release, angle of release and speed of release. Nice and easy, but when it comes to the applications, this is where students lose the mark. So let's make sure we can explain and apply. So here we go. So the height of release, the higher above the landing area that you release the projectile, the further it's going to travel. So it says on there that the greater or higher the release height, the greater the horizontal displacement, the further it will travel. So make sure you've got some examples. In things like shot put, we will make sure we release it well above the landing area. So we start from the shoulder, don't we? But then we will flex at the shoulder, extend at the elbow to make sure we get a nice high release point, because the higher we release that shot put, that projectile, the further it's going to travel. We're going to get a better score, we're going to get a better distance. The angle of release is a little trickier in the fact that there's a few factors that affect the optimal angle, but really what a coach and a performer need to do is determine the optimal angle of release to achieve the greatest horizontal displacement, the greatest distance. So there's three examples that I'm going to put there on the board for you. So you've got a long jump, you've got a netballer shooting in netball, and you've got a shot put. There's three kind of clear things that are different between those areas, and it's all to do with the landing height and the release height. So if we have a quick look at the long jump to start with, when the landing height is equal to the release height, so if you have a look at the long jumper there, they land in the pit, but the release height is where they've taken off from the takeoff board. It's level, okay? So let's make a note here, when the landing height is equal to the release height, the optimal angle of release as they take off of that takeoff board is 45 degrees. Okay, so the optimal angle of release is 45 degrees. It's slightly different for something like netball, so you're underneath the post, or basketball where you're underneath the post, or it might even be a bunker shot in golf, so you're in the bunker and you have to get the ball up and onto the green. So if we have a look, when the landing height, I know the ball doesn't land on the net, but you're wanting it to go, level with the net to fall in. So when the landing height is above the release height, the optimal angle of release is above 45 degrees. Okay, and then if we have a look at the last one, something like shot put, so you're releasing it at your shoulder, it's landing on the ground. So when the landing height is below the release height, the optimal angle of release is below 45 degrees. So just make sure if you get a question in the exam about horizontal displacement and about the factors that affect it, do make sure you give some applied examples of the optimal angle of release, because it varies depending on the situation. So if the landing height is equal to the release height, optimal angle of release is 45 degrees at takeoff. When the landing height is above the release height, something like a netball or a basketball shot or a bunker shot in golf, where you've got to get kind of almost loop the ball of the projectile up and in, the optimal angle of release is above 45 degrees. And when the landing height is below the release height, the optimal angle of release is below 45 degrees or less than 45 degrees. And then just if we nip back up here again, there's just one final factor that we haven't looked at yet, and this is the speed of release. So the greater the release velocity of a projectile, the greater its horizontal displacement is going to be. So in other words, if we release something faster, it will go further. And there's a number of things an athlete or performer can do to achieve this. So if they apply more force, they're going to have a faster release. So if they apply more force, they'll have a faster release. But also in events like discus and shot put, quite often, well, all the time, you'll see your elite performers, when they're doing the discus or the shot put, they will do kind of almost like a rotation or a shift across the turning circle. In shot put, we call it the O'Brien technique. It's that spin before you release. And what they're trying to do is build up momentum. And if they build up momentum, it means they can apply more force as they release that projectile, so it's going to go further. So again, make sure you've got some of those bits and pieces up your sleeve. If you think about something like a long jump, you know, you get a nice fast run up, you get that speed in the run up, and that then will transfer as momentum as you go to take off. So those three things there need to be considered when we are looking at trying to get or achieve the furthest distance or the greatest horizontal displacement. Okay, and then the last little bit is about parabolic and non-parabolic flight paths. So let's start off with a parabolic flight path first of all. A few questions, and again, on your kind of mind maps or your whiteboards, write these down. What is a parabolic flight path? Can you draw one for a shot put? And can you explain why a shot put follows a parabolic flight path? What is it about the shot that makes it follow that parabolic flight path? Again, if you just want to pause it while you make your notes, and then you can come back and check you've got your answers right. So here we go. What is a parabolic flight path? So a parabolic flight path is a symmetrical flight path. I've drawn one there on the board for you in that burgundy ready colour. And you can see, because we've done it for a shot put, the release height on the left is higher than the landing height because you release it from your shoulder. Okay. So that's a parabolic flight path. It's almost like a rainbow shape or an arc shape. Can you explain why a shot put follows a parabolic flight path? Well, if you look at the picture there, the shot put has got a very large weight force. This is because it's very heavy. And when we throw it in the air, because it's so heavy, it moves relatively slowly through the air. And because of that, air resistance is considered to be negligible. In other words, it doesn't really affect it. So the only thing that really is affecting that shot put as it flies through the air is its weight. So as it sets off, gravity is going to be trying to pull it down. So make sure you've got those notes, and that then takes us on nicely to this little bit here on vertical and horizontal velocity vectors. So when you throw a projectile, whatever it is, you give it some vertical velocity, so some upwards velocity, and some forwards velocity, some horizontal velocity. And what you might need to do in an exam, and this hasn't been up for a while, is draw on the horizontal and vertical velocity vectors onto the parabolic flight path and make sure you can explain them. So again, if you just quickly pause this, on the parabolic flight path, draw on the horizontal and vertical velocity vectors as you think they stand, the little arrows, and then if you pause it and come back, I'll go through the explanation. Okay, so you should have got something along these lines here. So as we release, let me just get my pen one sec. There we go. So this here that I'm pointing to is the release point. So as you release that shot put, you give it some upwards velocity and some forwards velocity. So you give it some vertical velocity and some horizontal velocity. Now, what you'll notice, and I'm going to do the horizontal one first because this is the one that's a bit quicker and easier. What you should have on your diagram is that horizontal vectors are all the same length. This is because once we've released that projectile and it's moving slowly through the air resistance doesn't affect it because the weight force is the dominant force. It's moving so slowly, air resistance is hardly touching, it's hardly having an effect. So the horizontal vectors, the forward red arrows, will all be the same length, and this is because air resistance is negligible. There you go, so that's the reason why. So all the way through from start to finish, you should have forward horizontal arrows that are all the same length because air resistance is negligible. Okay. If we then have a look at the the upwards arrows, the vertical vectors, we notice that we've got a large upwards velocity or a large vertical velocity. On release, because we want to give it that height to get it to kind of launch it into the air. I may need to make this a bit bigger, 1 second. But you'll then notice that the vertical velocity vectors start to decrease. Why do you think this is? The vertical. And this is because gravity is acting on the vertical components. It's acting on that weight force. It's slowing it down in an upwards direction. So the vertical velocity vectors decrease on the way up because gravity is acting on that vertical component. We then get to the peak of the parabola. I'll show you where that is in a sec. Show you on here. For that. So if we look at the peak of the parabola here, okay, you can see that we have got still forwards velocity, so we've still got some horizontal velocity, but our vertical velocity has reduced to 0 because gravity slowed it down that much. So at the peak of the parabola, vertical velocity is 0 as gravity has slowed the vertical velocity so much. And then you'll notice on the way down, the vertical velocity arrows start to pick up again. They start to kind of increase their velocity, so the arrows get longer. And the reason for this is now that gravity's pulling that projectile, pulling that shot down to the ground. Okay, so on the way down, vertical velocity increases as gravity acts on the vertical velocity. So basically, or shall I put acts on the projectile, acts on the projectile, pulling it down to earth. You'll notice that if you look at either side, so the arrow here is exactly the same length as the other side. So the arrow down is the same length as the opposite arrow up. The arrow down is the same length as the opposite arrow up. And the reason for this, or this is the reason why we get a symmetrical flight path. So the other thing that you'd need to note is that the arrow, or the vertical velocity, is exactly the same magnitude on each side of the parabola or the arc, okay, and the arrows will be the same length but opposite directions. And then your longest arrow is just before landing. And this is as the shot tries to fall almost below gravity, it kind of dimples down into the earth. So the shot tries to fall below gravity. It's trying to keep on going. Okay, so just make sure that you know the different bits of the, let me just move this across here, the different parts of the velocity vectors, and you can explain them and you can draw them and you understand what's going on and all the rest of it. So make sure you've got all that information on there as you go through. And then last but not least, let's just look at the shuttlecock up here. So if we have a look at the shuttlecock here, let's make that a bit bigger. That follows a non-parabolic flight path. And the reason it follows a non-parabolic flight path is because a shuttle is very light. So at the start of the flight, when you hit it with the badminton racket, so at the start of the flight, it's got a small weight force because it's really light. But that means when we hit it, we can hit it really fast. So when we hit it fast. And when we hit it fast, it means it smashes through the air. So it's got a large air resistance. If you think about it as it's hit, that large air resistance is going to slow the shuttle down. So as it's struck, it flies through the air, it slows until actually when it gets to this point here, hang on. When it gets to this point here, it's slowed down so much. Slow until weight becomes the dominant force and causes shuttle to plummet to the ground. So that kind of sums up everything that you need to know about in terms of horizontal displacement and projectiles. Obviously, you've got your class notes. You've also got your revision notes. And if you go onto Teams, you've also got all the questions and all the answers that have been asked so far on these areas. So do have a look and do have a practice. But that sums up everything that we need to know there for your parabolic flight paths. And if you need any of the extra revision notes, go on to the Padlet and they are all there for you.